Dear students, I am going to teach you now how to utilize Cauchy's residue theorem. Okay, now we have seen in the last lecture, you saw how we can calculate integrals using this theorem. The calculation is surprisingly simple. You have, suppose, a loop integral along a closed curve called contour, and then this is the function whose integral you want. Then according to this theory, this function, the integral of this function is simply 2 pi I residue at say z equal to z1 plus 2 pi I residue at z equal to z2, 2 pi I. That means simply it is basically z is equal to z3 plus dot dot. Now it simply means that you have simply to calculate residues. Evaluating contour integrals using Cauchy's residue theorem is basically finding out the residues. If you are able to find out residues, then you have evaluated the integral. The only factor that you need to multiply those residues, sum of those residues, is 2 pi I. So simple, but it is simple only if you are able to find out residues of a function. Now, how to find residues? There are for residues. There are two options available with us. If you are finding residues at a pole, then there is one formula for that: residue at a pole. Residue at a pole. At a pole. For this, we have one formula. And if you are finding residue at an essential singularity, residue at an essential singularity, then you have no other course except series expansion of fz in Lorentz series. In Lorentz, that means fz we should be able to expand Lorentz, this given function, in Lorentz series expansion. This a function in Lorentz series expansion, this can also be applied to this, but often this Lorentz series expansion is a cumbersome thing, so this option has a simpler that method of finding residues, and that simpler method is this derivative in Taylor's theorem. Derivative of Taylor's theorem. What does that mean? It means that suppose you have a function which has a which has a pole at A. This means z equal to A is a pole. Okay. You want to find residue at A. At this pole. Let us think that order of this pole is n. Okay, then we have seen in the last lecture, we saw that residue in this case is given by residue is equal to residue at z equal to A is equal to 1 by n minus 1 factorial. Then we have limit z tends to A. Then we have derivative n minus 1th derivative dz n minus 1 of now it has to be seen of what? Of z minus A. Z equal to A is singularity. Z equal to A means singularity. If we take we transpose A to this side, then we get z minus A. Z minus A is singularity factor. this is singularity and this is singularity factor. We have to multiply the given function fz. Given function fz is to be multiplied by singularity function. Singularity function is singularity this singularity factor z minus a raised to n, pole order of the pole. Okay. This is the formula. Now, if pole is a simple pole, there are now two choices. If pole is a simple pole, then this formula becomes much simpler as compared to this. If pole is a simple pole, so we will use that formula for simple pole. But that formula for simple pole we will deduce from this. Say suppose a pole is simple pole, that means its order is 1. So here we will get 1 minus 1, that is 0. So in case of residue, I will write it residue for a simple pole. For a simple pole SP, simple pole is 1 by, simple pole means order is 1, 1 minus 1, that is 0 factorial, which is 1. Limit, it is an interesting thing, 0 factorial equal to 1. Okay, now limit z tends to a, z tends to a. Okay, now see, if n is 1, then this becomes 1 minus 1, 0 d0, this becomes 0. So no need to differentiate this. You just have then to find limit of z minus a, n is 1, so fz. This is simple. For simple pole we have this, no need to write even this. So we have simply this formula for simple pole. We will collect it here. Simple pole, for simple pole, residue is equal to, I will not write residue at. It is, since it's a simple pole, it has only one pole, so it has order 1. Sorry, and you mean when you write residue, you mean at simple pole. Now there may be more than one simple pole, but this procedure will be same. Now we have first thing that we have to write limit z tends to a, simple pole at a, z tends to a, z minus a into fz. So we will remember this for a simple pole. But for other poles which are not simple, where for example order is 2, it will be, you cannot, then it is 2 minus 1, that is 1 factorial, that's 1, but you cannot now ignore this. If order is 2, 2 minus 1, that's, you have to differentiate it and at least once. So what to do in that case if pole is not simple pole? If pole is not simple pole, then pole is not simple pole, then keep this thing written with you. If pole is not simple pole, then do this thing. So follow this procedure. Pole is not simple pole, so this is your function fz given. Multiply, first of all, generate a new function, call that gz. Gz is a new function that is to be generated from fz. How? You have to multiply gz with singularity factor. Which singularity factor? That where the pole is. First of all, let the singularity be z equal to a at a. It is a pole, but it has order. Now it does not have this, z minus a is not raised to 1. It has some power other than 1. That's why it's called this pole of higher order. It's not a simple pole. Now what you have to do, you have to take this singularity factor, multiply fz by singularity factor, but keep one thing in mind. The singularity factor must have the same order as the order of the pole. If a pole is of order n, singularity factor must have n. So the first step that we remember while dealing with non-simple poles, so we will remember, in that case we have to create a new function gz from the old function fz. How? By multiplying fz by singularity factor. So new function nf is equal to singularity factor into old function, OF, old function. You can keep this thing. Once you do it, everything is then simple. How? See, differentiate this simple function. Differentiate. How many times? Exactly as do this power n. Now, you may find it a little bit difficult. You may say, well, sir, this will become very difficult when we multiply it by fz. But you have not seen one thing, that is fz has at least I know one thing about fz. I don't know exact this form of fz, but one thing I'm sure, 100% sure, that is fz has in its denominator z minus a raised to n. It may be having something else, and in most of the cases it will be having something else, say z minus z plus say I, for example, a factor like this. Now, if fz is this, when you multiply this fz by this, this singularity factor is removed. It is removed, completely removed. So you can remember it like this. You can remember gz like this. Let gz be that part of fz which does not have this in the denominator. What is that part of fz which does not have this singularity factor in the denominator? It is 1 by z plus 1. That the same thing can be obtained by this. We can write gz is equal to z minus a raised to n into 1 divided by z minus a raised to n into z plus I. Okay, then this and this can be cancelled, and we get gz is equal to new function is 1 by z plus I. You could have directly, if you, after some practice, you will be able to directly write this 1 by z plus I, because this you are cancelling here. So now this is my function gz. Now new function gz is equal to 1 by z plus I. Differentiate it. How many times? As is this number. If it is 2 times, if it is 3 times. So let me say it is, suppose 2 times. So I will differentiate it first. G dash z will be equal to, when I differentiate it, I have to rewrite it as z plus I raised to minus 1. And then after differentiation, it will become minus 1 z plus I raised to minus 1 minus 2. 1 second. G double dash z is equal to minus 1 into minus 2 minus 1 into minus 2 into z plus I raised to minus 3. So this is our second order derivative, and order of our this pole is 2. You stop here. You have to do only one thing now, that is where is this singularity located which you are dealing with right now? It is located at z equal to a. Z equal to a. So put z equal to a in this. If you put z equal to a, you will get value of this will be minus 1 minus 2, that is 2 into z a plus I minus 3. This is the value of the derivative at the location of the singularity, that is z equal to a. Now substitute this. Now this is the look now at this formula. You have already calculated this whole thing. You have differentiated this. After cancelling out this factor, you differentiate it. Now, then you put z equal to a there. You got this whole value. Then you have just multiplied by 1 by n minus 1 factorial. So we will remember, for a simple pole, our formula will be this. This will be our formula. In both cases, you can remember one thing. That is, In one case, you have a simple this singularity, simple pole. So you have z minus a raised to power 1. You are multiplying fz. So you can see here. You are multiplying fz by z minus 1. You are multiplying fz by z minus 1. Z minus a, sorry. Z minus a, z minus a. In both cases, you are multiplying fz by singularity factor. There, singularity factor is power 1. Here, singularity factor is power n. That's all. That is what I said. New function is singularity factor into old function. The only difference between this and this is that here you substitute z equal to a directly without any differentiation. But here you differentiate, calculate the appropriate derivative, and then substitute z, give the value of a to z. That is the difference. I hope this might help you, and it will make your this procedure very simple. You just remember one thing. You create a new function by multiplying old function by singularity factor. Once you do that, you have finished half of the problem. So we need not we need not worry about this calculation of residues. But as I told you, this procedure does not hold. It is not valid with essential singularities. Then what we do if there is an essential singularity? Let's first consider such a case. Say we have this case. I will be dealing with an essential singularity, and essential singularity is this. I have a function. I have this c. Then I have z power sine 1 by z. That this is an essential singularity. Z equal to 0 is an essential singularity. Here, that will become clear if you expand this using Taylor's series expansion. That means L is this Lorentz series expansion. You know the formula for sin x. For sin x, we have x minus x cubed by 3 factorial plus x5 by 5 factorial, so on. So use that here and you will get z4 into this much z 1 by z. In place of x you have 1 by z minus 1 by z cube into 3 factorial plus z cube into 3 factorial plus x5 is 1 by z5 into 5 factorial plus minus dot. If you multiply this, you get integral this z4 when multiplied by this, it is 1 by z, it is z cube. Then you multiply this by this, you get minus z by 3 factorial. Then this by this, you get 1 by z raised to 1 by z 5 factorial plus dot. Now dz okay, dz okay. Now you have this expression. You can see yourself that this from this term onwards we will then get z square, z and other powers, higher powers, but higher negative powers of z. For example, there another term will have z equal to here you will be having z equal to 7 and so on. Now, since there are infinite terms which contain z in the denominator, hence this z equal to 0 is an essential singularity. You cannot remove it. Now, what to do? In this case, you have to identify directly identify the term which has whose coefficient is the term -1, n equal to -1, and that term, and then the coefficient of that term is c -1. That is the residue. So residue of this function, this fz, residue of fz, while fz means this residue of fz at z equal to 0 is here coefficient of coefficient of n equal to -1 term. Now look at this series and search for n equal to -1 term. You have n equal to 3, n equal to 1. Here is n equal to -1. So what is the coefficient of this n equal to -1? 1 by root 5. 1 by 5 factorial. Therefore, it is residue here is 1 by 5 factorial. And in fact, you can now write therefore integral. You can write the value of the integral now. Z4 sine 1 by z dz is equal to that is equal to now residue 2 pi I residue at z equal to 0. Residue at z equal to 0 is 1 by 5 factorial. This is the value of this. But most of the cases that you will have, they will be having poles. Singularity will be a pole type. Now, with that thing, now one more thing that I would like to tell you, that is residue theorem is used for three main integrals. Residue theorem. One is residue theorem is used for three types of integrals. Two types. First of all, let us classify them into two categories. Complex integrals, like for example, you can think right now. You can think of this integral, just this integral. Suppose you have to evaluate this. It's a complex integral. You have z, complex number, complex function, and this is the value. This is how you do calculate it. Calculate residue and then do this thing. Now, the important thing, perhaps the more important thing about these complex integrals or residue theorem is that it helps us to evaluate real integrals. That means often what people think when we switch over to complex integrals from real integrals, we expect that complex integrals will be much harder than real integrals. Surprisingly, that is not true. In fact, the reverse is true. The converse of it is true. What is that? That complex integration is much simpler as compared to real integration. That is why real integrals are being evaluated, especially definite integrals. They are being evaluated using this residue theorem, and you will see here how they are this evaluated. We will take up two types of these real integrals. Two types of them. One will be this type, function fx divided by a rational function by gx dx. Now I have changed from z to this is z, this z, fz dz. Now here fx gx dx real. Now one of this type, then of another type, that is this type. You can have a function of cos theta, sin theta, cos theta comma sin theta, d theta, something like this. We will take up. We already have done this. That's quite easy. You can yourself now do these things. Now we will go first to this type of integral as an example, and then to this. While using these, both will be these real integrals. While using these two types of integrals, while evaluating them, we will need a useful lemma known as Jordan's lemma, that we must first before taking them up, we must have an idea, a clear idea of that. Then only we will understand these. Although we will not in the final, this when you go for this solving the problem in examination, you will not need that. You will not need to write that, but you need to understand what you are doing. Now let us go to see what I am talking about. Here is a brief, that we can say a brief digression, that is we have suppose a path like this, along which a function fz is defined at every point. Fz is defined along this path. I have to calculate line integral of this path. Line integral of this path along C. C is not necessarily closed. It can be closed, but it need not be. For example, how do we calculate this line integral? Line integral is calculated by dividing the path length into these elements of length. Small elements of length. Suppose each element of length is of size delta z. Delta z. Okay. Then what we do, we choose one such element, say this element, and let zi be the zi be value of z, value of, say, yes, of course it can be z, value of z at this location, central value of z here, and fzi be the corresponding value of the function. That means value of the function at this point. Where have I chosen the point zi? I've chosen it between two limits, in between two limits. That's not must, that's not the only choice. You could choose it at the start of this interval, you could choose it at the end. That's not a problem. But let's settle on some one, and that should be constant for all of these, same for all of these. So let at zi, function value is f zi. Then what we do, we multiply this function value at zi by the length of the line segment there, zi, f zi multiplied by zi. So far as delta zi is concerned, it is same for, we usually take it same for all the elements. Now this is called little line integral. Line integral from this point to this point of fz. Why it's called line integral? Because you are multiplying it by length of the line along which you are calculating this. Now what you're then doing, what you do, you use take these products function into delta z at this calculate them at every this line segment, these small line segments at their centers, and then add them up. If you add them up, the quantity that you produce, let me denote that by j. J will be then I is equal to 1 to n fzi delta zi. That means I am adding this product plus this product plus this product plus this, all the products from one end of this to the other end. So that's okay. Now next what I am going to do, I am going to now take modulus of this, absolute value of this. Let this be like this. Absolute value of I is equal to 1 to n fzi delta zi. Okay. Now you might be knowing that absolute value of sum is less than sum of absolute values. If you don't know it, it is not a big deal to convey, to show you how this is true. Suppose you have 2 plus 3. So here you have absolute value and closing sum. Absolute value and closing sum. Now this is equal to plus 2 plus 3. No problem. You can check it. 2 plus 3, 5, mod 5, 5, mod 2, 2, mod 3, 3. So 5 equal to 5. But what about this 2 minus 3? Is 2 minus 3 equal to 2 mod 2 plus mod minus 3? Let's check. Let's see. It is mod 2 minus 3. That is mod minus 1, which is 1. So left hand side is 1. On the right hand side, you have 2 plus 3, 5. This means that the sum of the absolute value of sum may be equal to sum of absolute values, or may be less than sum of absolute values. So we write it like this: I equal 1 to n. Now sum of absolute values not equal to this, rather that will be greater. This sum will be greater than this side. So you have fzi delta zi, sorry fzi delta zi. Okay, now next is that if you have product of absolute values, suppose you have 2 into 3 absolute value of product, that is exactly equal to absolute value of these numbers which form the product. You can check here: 2 3 is a 6, 6, check here 2, check here 3, 2 3 is a 6. Now do one more thing: 2 into minus 3 is equal to 2, that is mod 2, that into mod minus 3. Now multiplying 2 3 is a minus 6, but mod of minus 6 is 6. 2 into mod of 3, minus 3 is 3, 2 3 is a. So what do we see? We see that product, this absolute value of product is equal to product of absolute values. That means this is equal to this and this. They are equal. There is no difference. I is equal to 1 to n. Now fzi delta zi. Good. Now this much. Let us turn to another page. J is equal to, J is then less than, see, J is less than this quantity, less than this. Let this be, say, 15. J is less than 15, but 15 is equal to this. 15 is equal to 14 plus 1, for example. So J is less than this. When you write this equal, this means these two are equal, not that these two are equal, and this is less than this. So you have this situation here: summation I equal to 1 to n. Then we have f zi into delta zi. Now next, what is there? Let us see what is there for us. We have, this was our curve C. On this curve, this is the value of the function at some point, say zi point. Zi function value is this fzi. There are some functions which are bounded from above. That means they cannot cross a certain limit from above. For example, sine theta. You know, sine theta, maximum value of sine theta is 1. It cannot cross 1. Now, this means that, for example, suppose now take 1.2 a number. Sine theta is always less than 1.2. Similarly, if this f zi has a number, if there is a number m, such that this modulus of this absolute value of f zi is less than m, then we can write here j is less than or equal to I is equal to 1 to n m this, because this is m is greater than this. It is already this is greater than this. This means that m will be greater than this g, more greater, this greater than g. So I write here m and then delta zi. I do one thing now. For a moment, keep it there. Delta zi. Now I can write this m can be written here because it is a pure number. It doesn't have any index. J is less than or equal to m, and then this I is equal to 1 to n delta zi. Now if you let n tend to infinity, that means number of these zi's becomes infinity. Then size of each delta zi will tend to 0. When you add up all those little elements, then what happens? This becomes the length of this curve, because you are adding all those. You may ask me, sir, why do we need n tends to infinity for that? Even if we add them, suppose you have this. Even if I divide this into 1, 2, 3, 4, 5, 6, 7, 8, 9 pieces, and I add up these 9 pieces, even then it will be equal to this length of this. But see, when we talk of delta zi, we don't mean this line. We mean direct this. Suppose, for example, you have this is the curved line, and if I take delta z, this delta z will be invariably less than the actual length. If you are taking delta z as straight line, now delta z will be invariably less than this. So how to you are missing, in this case you are missing some length. In order to not make any error, what we have to do, we have to, instead of taking such big delta z's, we take such small delta z. One here, straight here, then another straight here, then another straight here. For that matter, you need to take extremely small size of each delta z, extremely small size, and then add up. In that case, no length will be left off. So this will be, and that case, it will be total length of the curve. But when you take n tends to infinity, at that point this sum becomes integral. J is no more now sum, it is integral. So we have integral of fz dz, mod of that, of course, mod of that is less than m into this is L, length of this. Now you have to understand this. J, you go back for that. Go back and see what was J. This sum. But when you let n tend to infinity, n tend to infinity, what will happen? This will become, then the sum will change into integral. That is what I did. And the final result, what does this final result tell me? It tells me that fz is such a function that its integral, absolute value of its integral, is bounded. We call this bounded, means there is a number. We can say, well, even if I don't know this integral, I know one thing, that this integral will not cross this limit. It will be always less than or equal to ml. This is called ml bound. And some people call it Jordan's lemma. Now we will be using this. We'll be using this in where you will see yourself. Now let us take, as I told you in this previous page, I told you, not here, but here, yes. Suppose we take first this example. An integral of this example. This is our example. In order to make things simpler, I will first take fx equal to 1, just to make things simpler, so that you are able to understand the basic philosophy. Once you understand basic philosophy, you will then be able to find the you will be able to find just evaluate more complex functions. Now, the basic philosophy. Suppose we have to evaluate this integral, and this is real integral. As you can see, real integral, we have integral minus infinity to plus infinity 1 by 1 plus x square dx. You can see suddenly variable has changed back to our familiar x, and you have to evaluate this. Now, of course, this integral is so simple that you will easily identify this as it is tan inverse x. So, the purpose of starting with this is just to take the simplest possible thing, because the ideas that I will be using, those ideas are, they need some understanding, quite a bit of understanding, and I just want to make that understanding easier by taking an easy integral first. We'll then modify it, of course. We'll then modify it. Let's begin with this. To begin with this, what we do here is our procedure. What is our procedure? Remember that this is our integral. Let me call it I. Let me call this integral I. That is, its value is I. What do? I construct a new integral, which is a complex integral, by copying this. How? I write J for that complex integral, and I write, instead of this minus infinity to plus infinity, I take a loop integral along a closed curve. Now, the definition of this closed curve, etc., this is, since it is closed, hence it is called contour integral. And sometimes this is also called, this evaluating these integrals is called contour integration. 1 by 1 plus z square dz. You can check, you can see. But as you know, for evaluation of this, I'm going to evaluate this, and that will give me this. You need just to watch and see, but at the same time understand each step. I take this one, since I have a complex integral now, and this is to be evaluated along this loop, I need to determine this loop, what this loop is. The loop should be such that there should be some convergence disk for our function, so that I can integrate it. Otherwise, if there is none, I cannot. So let us take this thing. This is our complex plane. Okay. And in this plane, what I do, I see, first of all, I analyze this for singularities. You can see yourself 1 by z square can be written as 1 by z. It can be written as, let me write it as z square plus 1. Z square, instead of 1 plus z square, I write z square plus 1, no problem. That gives us z plus I into z minus I. Two factors, you can check. Z square, and this is z plus I, z minus I, sorry. Z plus I, and then z minus I. Z minus I. You can check. Z square minus I square. Minus I square is, that is 1. So z square plus 1. So these are the singularities. So the singularities of this function are, let me first write it like this. In terms of these, we must write the function in terms of this, what we call this singularity factor. 1 by, I write 1 by z plus I into z minus I. Now, dz. Okay, now what I do, I take this. See, I take this. See, where are the these poles? One is at this I plus I, at this plus I. Another is, let me make it a little bigger, because I have to show certain more things to you. That is, let this is I, let this be I, and let this be minus I. Here is minus I. Okay, then I will choose deliberately a loop that goes partly along the real axis, partly because I have to evaluate this real integral. This must come out of this. This must come out of this. So this means that this loop C should have a part along this real axis for real x integral, a part along the z plane for this complex part, for this complex part, and that I will choose. I will first go with a function whose this a curve whose radius is r, so that this is minus r, this is plus r. From plus r to minus r, I will choose it like this, a semicircular curve, this, and then going from this to this. That means if I label it, it is minus or say a, and call a to be this, minus or to a to be a closed loop enclosing one this this singularity. The other singularity is out of it. Okay. Now let me first deal with this singularity, z equal to I. Now, what is the value of this integral? What is the value of this integral along this loop? Along this loop. See, one thing that I would like to tell you, that is, it's not must that you take this loop like this. You can choose loop from bottom. Then this will not come within the loop. Only this will come within the loop. Our loop encloses this singularity, so only this singularity will matter. I need not calculate residue at this because it is not within the loop, and the value of the integral along this loop, for that only this singularity is important. So now I take this z equal to I singularity, that is this z equal to I. This is that singularity factor. This will give me z equal to minus I. Now, if I take this, now I know j is equal to 2 pi I residue of this function fz, residue of f at where, at z equal to I, z equal to I, this z equal to I. Now I have to calculate residue of the function at z equal to I. Since z equal to I is a simple pole, it is not a pole of higher order, it is simple pole. So I will use simple formula, and simple formula for that is you can once again see that simple formula for that is simple pole limit z tends to a, z minus a, fz. First of all, what do you do? What we do is we multiply this function. Our function is this is our function fz. Fz is this 1 by z plus I into z minus I, and I multiply this fz by the singularity factor, that is z minus I. So my new function is not this f, rather it is z minus I into fz, z minus I into fz. The power here is 1 because it is simple pole. Power here is 1. So it is, I have now 2 pi I residue, then z minus I, oh sorry, you have to take limit z tends to I, now it is limit z tends to I, z minus I into fz. Fz is 1 by z plus I into z minus I. You can see z minus I will go with z minus I. You are left with this. You are then having j equal to 2 pi I, 2 pi residue, 2 pi I residue j is equal to 2 pi I residue this z equal to I Now limit of this, what I have to do, I have to take the limit of this. Limit, that is 1 by, now z, I have cancelled this. Now take limit, put z equal to I here, then I get 1 by 2i. I plus I, that's 2i. 1 by 2i. So residue is, value of residue is 1 by 2i. 1 by 2i. You need not write residue now there. Residue, it should have been, this residue is, the actual form of this is that residue is equal to this. Residue is equal to this. Now, going back to this, I have divided by 2i. 2i, that 2 and 2 will cancel. I and I will cancel. Value of j is pi. So, whose value have we calculated? We have calculated value of this j. That j is this. That means I have calculated this value. Integral, loop integral of c, loop integral of c, fz, fz, that is 1 by z square dz. 1 by z square dz. 1 by z square, 1 by z square dz is equal to, I found it equal to pi. Now see what I am going to do. I will now, as you know, this is my loop, minus or to plus or, and this is this part of the loop, that's a or to minus or. This curved part of the loop we will denote by cr, and rest minus or to or. This. Now I will divide this integral into two parts. This integral, it is, one part is minus or to plus or, minus or to plus or. See, minus or to plus or, 1 by 1 plus x square dx. Then this, from this to this, it is cr, it is cr. Of course, you cannot write that that little circle here. It is this cr alone is not closed. Cr, then we have this 1 by z, 1 plus z square dz equal to sum of both these. So both these is equal to pi. Is equal to pi. Okay. Now you might ask me one thing, sir, why did you write this x here and yz here? Because minus or to plus or, y is 0. As you know, z is equal to x plus y. Now when y is 0, from minus or to plus or, y is 0, z is reduced to x. That is it. This gives me, this is my this real integral. Now I want value of this, but with one condition, that is this should be minus or minus infinity, this should be plus infinity. This means that I should have such a result which will give me this possibility option, that is, if r tends to infinity, and this integral goes to 0. If this goes to 0, see what will happen. Just by this r tends to infinity, this going to 0, we will have no this term here, and minus infinity here, plus infinity here. This there will be no such term, and pi on this side. And you see, the whole magic lies in vanishing of this integral. Now, will this integral vanish? Not only it will vanish, but only when r tends to infinity. But how? That I want to explain to you. Although you need not, in the examination, you need not prove it as I'm going to prove. You need not prove it. You can just quote that by Jordan's lemma, or it can be shown that this integral, as r tends to infinity, this integral tends to 0. Now see how do I know this thing. Let me first keep this, remember this equation first. I just need a magic result. Now for that result, let me go here. Here is our path. Okay, this is r, minus r, this is plus r, okay, this is I, this is minus I. Now this is that semicircular CR, CR. Okay. The integral that I wish would disappear, that is CR integral, this integral. Now let me see what to do with this integral. Here I have, just a minute. Now here, now not here, actually there, in on the next page. Now this is the situation. I have integral CR and 1 by z square plus 1 dz. I need to evaluate this, what this will be equal to. I know this is equal to this CR 1 by z plus I into z minus I. Okay, that is okay, that we agree. It can be written as this. Now see, I will show that this integral has a maximum value. Maximum value of this integral is equal to this length of this semicircular is pi r. Length of the full circle will be 2 pi r. So length of this is pi r. Pi r into another positive quantity. Those will form ml bound of this. Let me see. Let me show. Instead of speaking, that may confuse you. Let me explain this like this. You have this z plus I. Why is z plus I? Remember one thing that is very important. When you show in a complex plane, you say this is point z. This point z is it represents a vector. This vector. This is the vector represented by z. Complex number represents a vector because it has two parts, x and y part. Z is equal to x plus iy. Now, and this x part is this real part, y part is the imaginary part. I is the imaginary number. It is for a number, for this vector, it is not imaginary. It is as real. Y is as real as real part. What is the role of I there? Simply an orthogonal rotor. It turns this a line, a horizontal line, into a vertical line. Anyhow, we say that a complex number represents a vector. In fact, representation of vectors by complex number in a plane is a very important thing. Very, very important thing. It is there are only 3 algebras that allow for division of vectors. One of them is this complex numbers. Complex numbers allow for division of vectors. Then there is another that is called quaternions. They allow for division of vectors. Then there is another in 8 dimensions that is called octinions. These are the 3 algebras, the only 3 algebras that allow for division of vectors. Well, anyhow, that is a separate thing, part of Clifford algebra. Now let us go back to this. We have this z. Now this is z. Okay. Well, now what is I? Let me show now. I is this. I is this from 0. Every number, every complex number is to be interpreted from every complex number is to be interpreted from origin. Okay, now let us go to this origin. Z, if z is shown here, it means it is distance. We can say it is modulus, means this distance from the origin. Mod z means distance. And what does it is this argument that angle means? Theta mean? Theta means it is direction. It gives direction. Now, similarly, if you have I here, I means this distance. The absolute value of I is 1. That is 1. Even absolute value of minus I is 1. When you speak of absolute value, it simply means root of x square plus y square. Root of x square plus y square. When you have z is equal to just I. Root, what is it? X square. That is 0. 0 plus I, 1. 0 plus I into 1. That is x square, 0 square plus this 1 square. That is 1. Simply 1. So, with these preliminary things, now see. look at this z plus. Let me show you why. Suppose this is z here. So this is z. Then this is the vector z. This is vector z, and this is I, vector I. All vectors are to be measured from the origin. I, this is I. Where is then z plus I? Z plus I is the sum of these two vectors. But if I cannot show that z plus I like this is not z plus I. This is in fact z minus I. How do I know it? Because when two vectors, if you have A vector and B vector, they are being added. If two vectors are added, then this is A, this is B, this is their resultant. Resultant goes from tail of the first to head of the last. Look at this vector. Does it go from tail of the first to head of the last? No, it goes from head of the first to head of the last. Head of the first is actually, first is here, I, Z. Even if it goes from Z to I, it goes from head to head. Now it is not. It is not. It is something like this. Suppose you have a parallelogram, and then in that parallelogram you have this resultant R, and this is P, this is Q. Now see, these two, this is P, this is Q. You can see resultant goes from, sum goes from tail to head. Now instead of this, let us run a vector from head to head. Says this is the vector from head to head, and this has this direction. For example, this has this direction. What is the significance of this vector? What is this vector? I know this vector R is sum, but this vector I don't know. What is it? Excuse me, just a minute. What it is? Yes, let us see what it is. We know that this is Q, this is P. Let us call this vector. Let us call this this cross vector as, say, A, small a. So this is A. Now look, head of this is on the tail of this. Then according to vector addition, triangle of vector addition, P is sum of Q plus A. P alone is equal to Q plus A. Q plus A. And then Q, if you transpose Q to this side, you get P minus Q. P minus Q equal to A. This means that this A is the difference of these two. That is what it is here. This, which joins head to head, is difference of these two. Difference of these. This is Z and this is I. This is difference of Z minus I. I hope you understand this. And then, why is Z plus I? Z plus I will show you. This is I. Of course, downward it is minus I, but upward it's I. This is I. This is it is not Z. Z is this. This is, now see. This is what you call Z plus I. This is Z plus I. You can check it. Why? Because this is I. This is Z. Now, the resultant goes from tail of first to head of last. That is it. Z plus I. I hope you understand this. Now see, I want to maximize this function. I want to maximize this 1 plus Z plus. I want to find its maximum value. What I will know, I will tell you why. Because I want to find the upper bound of this function. What is the upper bound of this function? That means this can give me a hint where it's its upper bound. I will find maximum value of this. Give me maximum value of this. For maximum value of this, I should search for minimum value of this, minimum value of this, because when these are minimum, denominators are minimum, the function ratio will be maximum. So I will go for minimum value of Z plus I, minimum value of Z minus I. Now look, let us see first Z plus I. Why do you think will be Z plus I minimum? If I take a point now here, in order to save that this diagram from too much overwriting. Now suppose I take this. This is the loop. This is I. If I take, this is Z plus I. Z plus I. If I take it here, 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 where will be smallest? You can easily see it will be smallest at this point and at this point. at this, that means at this point smallest, at this point smallest. You can check if you doubt it, you can check by using scale and pencil. You can check it. This will be smallest at this, that means at or. So z plus 1, z plus I has smallest value at or, has smallest value at or, at z equal to or, at z equal to or, where z is equal to or. Now, because if you take this point, what is it? Z, its location, its position vector with respect to that is or. Remember, z is measured from the origin. Now you have z equal to or. Now z plus I has smallest value at z equal to or. But what is the smallest value? Smallest value, just substitute here or in place of z, you get or plus I. Or plus I is its smallest value. So, but what is the modulus of that smallest value? Modulus of that smallest value will be, that will be root of or square plus 1. So or square plus 1 is the smallest value of modulus of this. Modulus of this, smallest value of modulus of this. Very good. A measure of modulus is a measure of size. Now, what about z minus I? Regarding z minus I, z minus I will be having smallest value at this place, because at that location z will be this, z from this to this z, and I will be this. So whole of I will subtract from z, complete I will subtract from z, you will be left with this much. So this will be lowest here at this place. Now if it is lowest there, then what is that lowest value? Since this has the coordinate of I r is the radius, and I, since it is on the imaginary line IR, so I will have to substitute here. For this I will have to substitute IR minus I. Absolute value of that will be this r square plus 1. Just 1 minute, let me take I out. I or minus 1. Sorry, this number does not have any real part. It has its whole part is this imaginary part. So its absolute value is this or minus 1. Or minus 1 absolute value of this. So z minus I has an absolute value of or minus 1, and z plus I has an absolute value of root 1 plus r square or r square plus 1. I hope, my dear students, you fully understand this. Now, why I am looking for the smallest values? Because when I substitute the smallest values here and here, I will get the maximum value of this. Now, in order to find that maximum value of this, now I go to this step, last step. Now, so integral fz dz cr is equal to, just a minute, fz dz cr is equal to 1 by this. Now sorry, this modulus of this will be, that will be equal to this, that is, just 1 minute. Yes, maximum value of this is what we found it. Maximum value of 1 by z plus I, that is root or square plus 1. Root or square plus 1. Just a minute. Root or square plus 1. Okay. I will have to substitute it here. Root or square plus 1. So root or square plus 1. First of all, just a minute. I had this. I have to multiply this. I have found maximum value of these two. Maximum value of this much I have found. But maximum value of this is that is the path length, that is pi r. So I have two factors. One is maximum value of this. It will be less than or equal to maximum value of this. Just 1 minute. This integral CR 1 by z plus I into z minus I, that, and then this mod del dzi or whatever it is. Now and integral of this, of course, sum of this. Now this factor is that is pi r, and this factor is Just we found it just now. 1 by this z plus I was in its place. I have to substitute this. I have to substitute z plus I in place r minus 1, or minus 1, or minus 1. Smallest value of this, or minus 1. Sorry, smallest value of this, or root of r square plus 1. That means this is the maximum value of this, and maximum value of this, that is into pi r. Now see, as r tends to infinity, what will happen to this? 1 by, this will be 1 by r, because r, when r is very large, r minus 1 is r, into 1 by r here again, because r square, that is much greater than 1, that is r again, into pi r. Now r and 1 r will cancel. Now see, if r tends to infinity, let r now tend to infinity, pi by r will tend to 0. This means that this value of this integral will tend to 0 as r tends to infinity. So that is how we prove it. And once you prove it, this integral is now gone. This is gone. This is gone to 0. But why? When we allowed r to go to infinity. This means that we got this value. Here is the value. This went to infinity, 0, with r tending to infinity. So result is minus infinity here to plus infinity, 1 by 1 plus x square dx. That is equal to pi, simply pi, because this vanishes. In the proof, you need not show this, all that I showed you, but in order to understand how did it disappear, you have to understand these things. Remember once again that what I did, I found maximum value of this, and I found that maximum value that goes to 0 as r goes to in. How did I find maximum value of this? By finding minimum value of this, and minimum values were here. Model, of course, by all these absolute values or modulus, minimum value of these, and then using those minimum values, I found this maximum value, multiplied, and I multiplied that by this path length. We have already shown that in that lemma. Now path length into these. After all, what are these dz's? These are path lengths, elements of path length, and when you integrate them, you get the total path length. That gave me upper bound of this. This was the upper bound, pi r into this, and in that upper bound, what I did, I finally let r tend to infinity. This one dropped. I got this, and since r tends to infinity, this goes to 0. That is it. So yeah, I have got the maximum value of this is, now you can see here, that is that with that since when r goes to infinity, this whole goes to 0, hence we are set free of this. We will in our another video, we will now take another example of this, and for the time being, this is sufficient for this video. Okay.